The right triangle trig we did last week, SOHCAHTOA, is great for solving the pieces of a right triangle, but most triangles aren't right. What we have here is an oblique triangle. That word is oblique. And that just means any triangle that isn't a right triangle. And so the ratios of opposite, adjacent, hypotenuse, and the sine, cosine, tangent we make from them, that won't help us anymore because there is no hypotenuse, there are no opposite and adjacent legs. We need something else. So what we're going to do is start with this oblique triangle. And in order to figure out how to deal with a triangle that is not a right triangle, we are going to make it into a right triangle. So what I'm going to do is draw an altitude, which is a word for it, a name for a perpendicular line from angle C across to the other side. Now, important that it's an altitude because that means that these are perpendicular, and we've got two right angles here. So now what I have are two right triangles, and I need to give that a name. I'm just going to call that H for the moment. Well, we can figure out how big H is if we have a little bit of information, because the triangle, I'm going to call this point capital H right there, that intersection right there. The triangle BCH is a right triangle, so I could use SOHCAHTOA to say that the sine of angle B is equal to the leg opposite it divided by the hypotenuse of that particular triangle, which is A, which means that H, let's say it this way, H is equal to A times the sine of B, if I multiply both sides by B. But over here on the right triangle, I can do a similar thing, saying that the sine of angle A would have to equal the leg opposite of angle A, which in this case is also H, over the hypotenuse of the right triangle on the right. And so here I could say that H equals B times the sine of A. Well, if H is equal to A times the sine of B, and H is also equal to B times the sine of A, that has to mean that A times the sine of B equals B times the sine of A. They have to be equal to each other if they're both equal to the same thing. And so what I have now is a relationship between four pieces of the oblique triangle: side A, side B, angle A, and angle B. If I know any three of those pieces, I can solve the equation by finding the fourth. So this is a really useful tool. This is going to be true for every triangle. And notice how it doesn't require the H in the middle there. That's not a part of this. So I don't need a right triangle in order to do this. I will say that we don't usually look at it this way. A times sine of B equals B times sine of A. What we do is if we divide both of these sides, if we divide both sides of this equation by AB, then what happens on the left-hand side is that the A's cancel out and we're left with sine of B over B. And on the right-hand side, the B's cancel out and we're left with sine of A over A. If we would have set this up the same idea, but instead drawn an altitude like this, and so angle C would have been an angle that we looked at, we would have come up with the same equation with angle C inside C. And so that relationship is always going to be true. While I'm on the topic of rewriting that altitude, that H as A sine B, I want to remind you that this is really completely unrelated to what we're doing, except it uses the same idea. The area of a triangle you probably remember the formula from your regular geometry class. 1/2 base times height is the area of a triangle. And so for this triangle, the base could be that side C, and the height is that H. So 1/2. I know I use the letter B, but I'm not talking about that B. I'm talking about the base, which is side C times the H. the area. If I take out that h and replace it with really either one of the two expressions for h that we had, it works with either one, we can rewrite this as 1/2 AC times the sine of b. And so that's another way to write the area of a triangle. And of course, it would also work no matter which altitude I drew, so I could kind of mix and match the a's, the b's, and the c's here, as long as the two sides that are being used, whose side lengths are being used, is not the same as the angle that's being used. So 1/2 AB sine C or 1/2 BC sine A. All three of these are three ways of writing the area of a triangle, which is really not that closely connected to what we're doing today, but it's related a little bit. So going back to our law of sines, we have that the ratio of the sine of A divided by the length of A is equal to it's the same fraction, the same ratio as the sine of B over length B. By the way, a quick note, you can also take the reciprocal of all of that and say that A over sine of angle A is equal to B over sine of angle B, which has to be equal to C over sine of angle C. You can use whichever version you like. Basically, if we're looking to find a measure of a side, I'll do the version with the sides in the numerator. If I'm looking to find the measure of an angle, I'll do the version with an angle in the numerator. So, looking at the 3 points I have here, we can now use this to find all unknown lengths and sides of side lengths and angle measures of a triangle that's not a right triangle. If, this is a big if, we can only use the law of sines if we have an angle side pair. For example, in the triangle you see on this picture, if I try to set up my law of sines, I'd run into a problem. I know that side A is 10 and side B is 8, and angle C is equal to 45 degrees, but none of these fractions would be fully filled in. Each one of them would have a missing hole. So if I tried to use side A over the sine of A equals 8 over the sine of B, which equals little c over the sine of 45 degrees, I can't use any of these ratios because all three of them have a missing piece. So there's no way I could write an equation that has three pieces filled in. What we need is at least one angle side pair. And we'll see that in our next example.